So today we're gonna have a special live session where we are going to review the recent contests in CodeHawks. So I don't know who among you gave a try to CodeHawks. Some of you probably are in the middle of the course. Some of you completed the course. Some of you tried out Audit contest in Code Arena maybe, or in Sherlock. So CodeHawks is the new auditing competition platform that Patrick Collins created, and there were 3 contests in the last week, I guess. Last week, they just finished like a few days ago, and I myself participated in some of these contests. So I thought it would be super cool to do like the previous live session that we had with the USSD contest. If you remember, it was last month, I guess, or like 2 months ago. And this time we're gonna go through the contests, each contest, and I will show you how the platform looks like, what the contest was about, what was the code base. We go through the code base, understand it together, and I will show you my findings, everything that I reported. So I'm gonna expose it to you, and we're gonna go through every single finding, understand it. You feel free to ask questions or give your comments, and I don't know, like, what do you think about every single finding? And right after, you will have the opportunity to share your findings. So if there are some things that I missed, because I also miss things, I'm not perfect, and it's a lot about creativity. Maybe there are some findings that you were able to find and I did not see, or you were able to exploit. So you will share your unique findings that you reported. So this is the CodeHawks platform. As you can see, it's very, very similar to Code Arena and Sherlock, if you're familiar with those already, but they're gonna have additional feature. They're gonna introduce a marketplace where someone can post a job offer, and then auditors can submit their offer for this job, and some kind of marketplace between auditors. But we will get to that later once we get to the escrow contract and the escrow contest competition. And we will start from the first contest. So the first contest is the Foundry DeFi StableCoin CodeHack Audit contest. It was $15,000 contest it ended 4 days ago. It was like one and a half week length. And it was very, very common. A lot of people decided to join because it's very beginner friendly. The codebase is actually a codebase that Patrick created, part of his Foundry course. So I don't know if you guys had a chance to take this awesome course by Patrick Collins, this 3 parts course. In the third part, you're going to create a DeFi stablecoin. And this is the exact code base that was here in the contest. So if you completed Patrick Collins course, you had some kind of advantage of other participants because you're more familiar with this code base and how the stablecoin engine works. So yeah, this was the code base. Now the stablecoin, this is the contest. This is the repository, the page for the contest, and it basically this code base is supposed to be a stablecoin like DAI. So we talked in the course about MakerDAO and DAI, and DAI is basically decentralized stablecoin. What does it mean, decentralized stablecoin? It's basically supposed to be pegged to $1, and it's backed up algorithmically by collateral assets. So people can deposit wrapped ETH, Bitcoin, USDT, USDC, other types of assets to vaults, right, through MakerDAO. And then they can mint, based on their collateral, they can mint those DAI tokens. And by market powers and those minting and redeeming logic, DAI always preserve $1 using oracles, using demand and supply, market forces for arbitrage. But this is usually how DAI and MakerDAO works. And this project by Patrick Collins is some kind of simplified version of MakerDAO and DAI. So you have like a contract where you can deposit other assets. You use external oracles. In that case, we use Chainlink to determine the price in USD for every single asset. And then based on your collateral of the money that you deposited to the system, you can mint those stable tokens, right? So everything makes sense. If not, please ask questions in the chat. So this was the stablecoin contest, a very small amount of Solidity line of code. Less than 300 lines of code, $15,000, and it was pretty beginner friendly. That's why many people, both of them are students that maybe wrote this code before, or not even students of the course that want to get started with auditing contest and find some vulnerabilities in small code bases, in simple code base. Looked at this one as a good opportunity to get started, and this is why I decided also to join and participate, so we can do these live sessions and I can help you guys get started with auditing contest, to provide this kind of educational content for you guys. So because it's always easier to start with those easier contests rather than a huge one of like $200,000 or $300,000, you know, the Tapioca DAO and the Maya DAO kind of contest that we have in Code Arena. It will be a bit more challenging to get started. So this is the contest. And first, before we go to the findings, I want to go like a quick overview through the smart contract in my machine, in my local machine, to show you, like, first of all, how the smart contracts look like. And second is how I approached the contest what was my auditing methodology, what kind of comments I left in the contracts, how I had my external markdown file to write audit comments, so you can get some kind of idea and see my auditing approach and skills and methodology of how I approach a new code base. So this is the code base. I obviously clone it from the GitHub. If you are completely new to auditing contest, you have the repository. So you can click here to go to the repo, and here you can clone the code to your local machine. By the way, I don't know if you knew that, but all the submissions by all the participants are public but anonymized, which means that the name is not written for every issue. But if you go here to the issues, you can see all the submissions. So it's 1,100 issues, 1,000 submissions. It's a lot of submissions. So don't expect, if you participate, to get a lot of money from this contest. It's more for your like getting started and getting the confidence, you know. Look at it more like an educational experience and learning experience to improve your skills, not as like a big financial reward, because many people participated. The code base was quite simple. There were not many vulnerabilities, but there were some vulnerabilities, and you can see there are more than 1,000 submissions. So the competition is quite high. So probably the reward won't be tremendous, but it will be some kind of reward if you reported a valid findings. And here you can see all the issues, but you don't see who reported what. So if you will search here, for example, Johnny Time, you won't find my submissions because it's on purpose anonymous. Also, the people who judge these issues, these submissions, they also don't want to be biased through one person or another, because if they check a submission by some non-auditor like me, like, I don't know, Pashov, so they might be more biased. That's why they decided to do the submissions anonymous. And it's another thing that Sherlock also started implementing to make the judging phase more fair for the wardens. So the issues will be public only once the contest is closed. So the way it works is that the CodeHawks team probably runs some kind of bot that scrapes all their submissions from the database and create issues on GitHub and anonymize the username who submitted it. And then I don't know how it works behind the scenes, but I assume that then they go through these issues, the judges, and check every single submissions and start to add labels on them, if it's a duplicate, if it's a valid or invalid issue. This is probably how it works. So these are all the issues. If you want to see your submissions, you can also go here in CodeHawks to my audits, and here you can see all my submissions for every single contest. We will get to that later. So here right away, my audits, and you can see all. It's by the way, the UX is much better than Code Arena and Sherlock, and maybe they can improve after they see this, because this is very nice view that shows all your finding, every finding, also the status, if it was valid or it was rewarded. So I mean, for a new platform, CodeHawks did a pretty good job. They have better features, in my opinion, than some the features that don't exist in Code Arena and Sherlock. All platforms are awesome, but really it's a very nice beginning for a new platform that comes and competes in this market. The issues that you can see here, if you open it, it's like the report that you submitted through the website. It's a markdown style report with everything that you submitted. So you have the summary, the vulnerability details, the GitHub link. So exactly like you submitted in the website, there is some kind of bot that scrapes it and takes it out and put it as an issue in the repository of Cypherin. That's how it works. That's how it works with Sherlock also. All right, so let's get started with the first contest, which is the stablecoin. So this is the stablecoin from Patrick Collins' Foundry course, and this is what we had to audit and see if we can find any vulnerabilities in the implementation of this over-collateralized stable coin. So in this repository, we have two main smart contracts under the SRC folder, as you can see. I will increase even the zoom a bit so you will see better. By the way, can you see well my screen? Like the code, the text, everything is okay? All right, so there are two main smart contracts and there are libraries, and this is the stablecoin, right? So like we have DAI, so this is the DSC, decentralized stablecoin, DSC, right? And it's a simple ERC20 burnable token. All right. So here it's basically inherits from ERC20 Open Zeppelin. You're already supposed to be familiar with that if you went through the fungible token crash course. It initialized this constructor in ERC20, and then we have two functions, burn and mint, right? It's ownable. As you can see, it basically inherits from ownable. We use Open Zeppelin, ERC20, and ownable. So we use Open Zeppelin in that case. Every time that I see Open Zeppelin or Soulmate, it's like a white box, so it's like trusted. So I don't check those contracts, but I check the actual implementation of the burn and mint function. And as you can see over here, the burn and mint functions are protected by the only owner modifier. So there is an owner to this smart contract that can mint and burn these stable coins. Now the owner, it doesn't mean that the owner is an EOA account. It doesn't mean that it's a wallet. It could be also another smart contract, which is what happens in that case, because the owner of this token smart contract is actually the DSC engine. So this is the smart contract that can mint DSC tokens. And the way it works is that there are certain rules where this contract can mint those tokens. Obviously, anytime someone wants to mint tokens, he needs to deposit collateral to this DSC engine before. So again, I will make a short overview of how over-collateralized stablecoins work, like MakerDAO and DAI. Basically, people deposit other assets like wrapped ETH, like wrapped BTC, like link tokens like USDC, USDT, and for every asset we have an Oracle feed, okay? So in that case, we're using Chainlink to get a price feed. So at any point of time, we can understand what is the price of wrapped ETH or wrapped BTC, and then we can evaluate how much money in terms of US dollars the user deposited. Now, what over-collateralized means? It means that basically, if user deposited $1,000, it cannot mint more than $1,000. So the collateral ratio is being determined by the protocol, by the contract, and in that case, it's 200%, which means that if you deposited assets that worth $1,000, you can mint 500 stablecoins, $500. So it always should be 50%. This is how it works also in MakerDAO. And in that case, the collateralized ratio should be 200%. Cool. So everything that I explained is actually described here on top of the contract, and the documentation of this contract is very well, because obviously it was written by Patrick Collins in his course, and he wanted to show devs how to write good and well-documented code. And this is very nice, because usually when you audit Codebases in Code Arena and Sherlock, There is no documentation. The code looks very like ugly. And in that case, it was actually pretty fun to read the code because the code was making sense a lot. And every function was documented very, very nicely. And here you can see all the explanation about what does it mean over collateralized and that it's similar to DAI. So everything that exampled, you can simply just read it from the comments and the docs that you have on the smart contract itself. So this is the DSC engine, and like I said, this is the contract that is responsible to mint those DSC tokens. These are some predefined errors that they're going to be probably used later on in the contract. Here we have that we use some kind of Oracle lib that was imported over here. Right, so we have here a Chainlink aggregator and Oracle lib, which is a lib that was written to wrap Chainlink and to use Chainlink to get those prices. We'll get to that later. So now we go back to the DSC engine, and we have here some constants, right? So you can already see, if you have like sharp eye, that I already started leaving audit comments, right? So sometimes it's issues, right? I have this Solidity Visual Developer with some customized colors. I also tweeted about it, and I add always those special comments while I'll go through the code. So if I see that we have here floating pragma, and floating pragma is an issue, then I actually add it, right? I write these comments, so later on I can go through all these bookmarks. I have also this one, which is like inline bookmarks, and I can go through all the comments after the audit. I will increase it so you will see. I can go through all the comments, info, issue, okay, like, you know, everything is labeled, and I can go later to assemble my report and my submission. So this is a very effective way to audit code using these plugins with inline bookmarks extension. Highly recommended. And now we're moving on, and as you can see, I leave also comments. So if there is something with, for example, this number, like additional price feed, and I want to add some additional comments to have some context about it. For example, this constant number is going to be used. Yeah, so this will be used to multiply the result that comes back from Chainlink, because Chainlink returns numbers with 8 decimals for certain assets, the prices. So they use this price feed precision to multiply the result to get it to 18 decimals. So I add this info while I figure it out and understand why they use it. I add those comments, so it will help me later on to understand the code better. So here we have more constant. Now this is the health factor, not factory, it's supposed to be health factor, and it's in 18 decimals, liquidation bonus, liquidation precision, liquidation threshold. We don't know what liquidation means yet, but we'll see in a second. Here we have multiple mappings. So we have the price feed mappings. These are the mappings that is responsible. So for every asset that we have supported in the protocol, what is the address of the contract that provides the price feed for this asset. This is the mapping that basically keep tracks of all the collateral that was deposited to the system. So it maps between user to token to amount. And this is basically how many stablecoins this user minted. So as you can see it, this is like the credit of the user, and this is the debt of the user. This is the credit because this is what he deposited to the system, and this is the debt. This is what he owns the system. Every token that he minted will be counted in this uint, in this mapping for this particular user. So you can look at these two mappings like credit and debt, and this is just an array of all the supported collateral tokens by the protocols. So we are going through like all the constants, the state variables. Here we have the token itself, right? So it's immutable because this is the address of this token. Here we have two modifiers, right? So this is also what I like in this code base, that all the function names make sense. So more than 0, it makes sense, right? It's a modifier that makes sure that the amount is more than 0. If amount equals 0, we're gonna revert with this error message. DSC engine needs more than 0. Pretty straightforward, pretty easy. Also here is allowed token, so we check if it exists in the mapping of the allowed tokens. Sorry, if it's in the array, I guess, mapping or array. Sorry, here in the price feed, I guess. Yeah. So it basically checks if the token address exists in the price feed mapping. so it has a price feed. If it doesn't have a price feed, it will be address 0 by default. So we know that this token is not supported by the protocol. And this is the constructor, right? So this is when deploying the contract, the administrator, the EOA account that deploys it, need to provide the token addresses, all the tokens that we can deposit to the engine, the price feed, so what is the Chainlink price feed to determine the price of the token, and the DSC token address, the stablecoin token address that this contract will mint. And as you can see here, we set all the mappings of the supported tokens and the price feeds. We add them to both to the array and to the mappings. And we also deploy, guys, we deploy here the stablecoin. So now you understand why this stablecoin was ownable, because the engine is the one who deploys it, and the one who deploys it by default gonna be the owner, because it's ownable and it's the constructor will set the message sender to the owner. So this DSC engine smart contract is gonna be the owner of the decentralized stablecoin, and it can mint and burn tokens. So not an EOA account, but a smart contract. Now here you can already see that I reported some issues. So basically, if it checks that the token addresses length not equals the price feed addresses length. So the length of these two errors should be the same, but they don't check here that one of them could be 0. So what if both of them are 0? What if the engine is being deployed without any supported collateral tokens? This is an issue, because this is a state that is not supposed to happen. Now it's in the control of the admin, right? Because he's the one that deploys these contracts, but the admin can make a mistake and deploy the contract without any items in those arrays, right? There could be an error, or maybe on purpose. So this is kind of like a medium issue, I guess, or low issue. I'm not pretty sure, but this is just something that I saw, and I right away wrote it as an audit issue. Also here we have no address 0 checks. So in the constructor, we get the address and we don't check that it doesn't equal to address 0. And later on, we cannot also update it. It's immutable. As you can see, the token address here is immutable. Even if it wouldn't be immutable, this contract is not upgradable, and we don't have a setter function. So basically, it could be address 0, and that's it. The contract won't be usable. We will have to redeploy it. That's why these both things are, I guess, either medium or lows, because once you make a mistake and you deploy it with wrong parameters, that's it. You will have to redeploy the whole contract again. So this is about the constructor. Now, this is the external functions now. This codebase is very, very good. Also, the test coverage is very good. So you have here a lot of unit tests and also a bit of fuzzing by Foundry. So we have also the fuzzing engine of Foundry. So it comes with a very, very good test base. And I will also show you how it helped me to find some issues just by looking at the test coverage of the project. A quick rundown through the functions. So deposit, collateral, and mint DSC. This is a function exactly like it sounds. Deposit, collateral, and mint DSC. This is the stablecoin. And it calls two other functions, deposit, collateral, and mint DSC. So the logic is being separated into two functions. And we send 3 parameters: the token collateral address, the amount that we want to deposit, and the amount that we want to mint. We can also call these two external functions separately. This is just a helper function if we want just to use it as one transaction, because if you want, you can only deposit collateral or only call the mint DSC token. But if you want to save money on gas and do it in one transaction, then you can definitely use this one. So let's start with deposit collateral. Deposit collateral gets the token collateral address and amount collateral, and it has 3 modifiers. First one is more than 0, is allowed token, and non-reentrant. Non-reentrant, everyone knows, right? It protects from reentrancy. If you went through the reentrancy chapter, it should be very obvious by now. More than 0. So more than 0, we saw the modifier before. It makes sure the amount is more than 0. Is allowed token, also we saw the modifier before. It makes sure that we are sending a token that is supported by the protocol, by the engine, and the amount is not 0. And what it does next, let's see. It updates the mapping. So basically, message sender deposited this token address, and this is the amount that he deposited. So it updates this mapping. It emits an event, and it tries to transfer tokens. It uses the transfer from function. We're already familiar with it in ERC20 to transfer this amount of tokens that was provided as parameter from the message sender to this smart contract. Now it takes the return value, and if it did not succeed, it reverts the transaction. So we need to approve the contract before to spend our tokens, before we call either this deposit collateral or this deposit collateral and mint DSC tokens. Now, this is another issue because USDT token, I don't know if you're familiar with it, but it's a token that does not return any value. It doesn't follow the ERC20 standard, which means that the transfer form value does not return any value. And by default, if we get this return value, this Boolean, and this does not return anything, this is always gonna be false. Because if it doesn't return anything, we're gonna get here by default false. So even though the transfer of the USDT token succeeded, still this success Boolean will be false, which means that if at some point this engine will want to deploy and support USDT tokens, you cannot add collateral tokens to the protocol, but you can deploy it with other tokens, right? Currently deployed with wrapped ETH and wrapped BTC, but maybe they will want to deploy it later on with USDT as well, or they will want to deploy it on another chain with USDT. And in that case, this deposit collateral will always revert, which means that no one will be able to deposit USDT to this smart contract. And the solution is to use safe transfer lib, because safe transfer lib is a library by OpenZeppelin, which you can use. You can wrap your IRC interface with this, and then you can use, instead of transfer form, you can use safe transfer form that actually checks if the transfer form function has a return value, and only if it has a return value, it's gonna, and it was false, it's gonna revert the transaction. So this is the way to overcome this issue, and this is a valid medium issue in my opinion. This is one of the issues that I reported, and we can also already go to the issues. And you can see here as medium, USDT can never be supported by the protocol, right? Because, and here I explain everything that I explained to you, because it's non-upgradable and it doesn't allow additional supported token, but it can be deployed with USDT as collateral, supported collateral token. In that case, USDT won't work because of this issue, and the recommendation is to use safe transfer and safe transfer from instead of just manually checking the return value and validating that it's true. Okay, now I'm not going to go through the right order. I'm just going to jump to mint DSC. So we went through the deposit collateral. Deposit collateral simply transfer the tokens to the contract and updates the mapping. And then we can call the mint DSC function, which gets the amount that we want to mint. It applies two modifiers, non-reentrant and more than 0. And basically, it's going to add to the mapping, to the debt mapping. Remember, we have a credit mapping and debt mapping. This is the debt, the money that we own to the protocol and to the contract. And it's going to add this to our message sender, this amount. And we call another function that calls revert if health factor is broken. So we will see that later. So basically, the health factor is what determines how healthy our position is. So it makes sure that we maintain this 200% over collateral in the protocol. So we cannot mint if we did not deposit tokens, or if we did not deposit at least 2x of the tokens that we want to mint. And after this function, if it succeeded and did not revert, then it actually tries to mint those tokens to message sender, and it reverts if it failed. So now we need to understand what is this revert if health factor is broken is. So it doesn't gonna allow us to mint tokens just that like easily, but it's gonna first calculate our health factor. Okay, health factor is simply like how healthy our position is, how much we provided assets and how much we took assets from the protocol. What is our credit relational to our debt? And this internal function is supposed to get the health factor. So we're going to jump to this health factor. As you can see, it's a private function, and it uses another function that's called get account information. So it sends the user is probably the message sender. Let's jump to the get account information, and it's simply going to return our debt and credit. Both of them should be in USD value. Okay, so if we minted 1,000 tokens, this will be $1,000 that. If we provided assets that worth $2,000, then this will be $2,000. Both values will be returned with USD. And now we go back to the health factor function, and we take these two values and we send it to the calculate health factor function. And the calculate health factor function is basically the logic where we calculate how healthy our positions are. So first, if we didn't mint any DC tokens, we return maximum. Basically because we didn't mint tokens, which means that we have positive health factor. Okay, so our health factor is legit, and that's okay because we didn't mint any tokens yet. Now, if we did mint DSC tokens, then we are doing some calculations over here. Let's see how these calculations look like. So we have the collateral adjusted for threshold. We have the collateral value of USD. We don't know how it's calculated yet. We will get to that later using chainlink process. But imagine this is all the assets that we deposit to the protocol in USD value multiplied by the liquidation threshold divided by liquidation precision. So this is supposed to be value in USD in 18 decimal points, like the DSC, because we need to normalize it to be with this total DSC minted, and we know that the DSC token is 18 decimals. Multiplied by the liquidation threshold, which is 50, right? 200% over collateralized. What does it mean that we multiply it by 50? And then we divide it by liquidation precision, which is 100. So basically, you see, as you can see here, I wrote here an audit info comment, so it will be more clear. So it's basically going to be 0.5 multiplied by collateral value in USD, or simply just 50% of our provided collateral, because this is multiplied by 50 divided by 100. So it could be also multiplied by 5 divided by 10. It doesn't really matter. So it will be easier for percentages. So this number is just, it looks very complicated, but it's not that complicated. It's just going to be 50% of our provided collateral, right? Because we're supposed to be 200% over collateralized. Then we return this number multiplied by IE 18, so like 18 decimals, divided by the total DSC minted. So why we multiplied by IE 18? This is supposed to be in IE 18, and this is supposed to be also in IE 18. So if you think about it, it will be, let's say we provided $1,000, so it will be 1,000 multiplied by IE 18. 1E18 multiplied by 50 divided by 100, so it's going to be like 50% of our collateral, multiplied by IE18 that we see over here, divided by the total minted DSC that is also going to be in IE18. So if we minted 500 tokens, then it will be basically this IE18 is being disabled. This will be like 50%, so it will be, instead of 1,000, it will be 500 multiplied by IE18. And in that case, it will be 1. Let's do it like this. I'm basically solving the formula, and it will be just 1 multiplied by IE18. This is in case that we provided $1,000 and we borrowed $500. So it's a bit complicated formula, but eventually it's in order to calculate how much we borrowed compared to how much we provided. And then it's going to return this value. This is the calculate health factor. And let's go back. We will go back to this function because there is an issue with this function, with the way that they calculate the collateral and the way they decide if the health factor is legit or not with BTC token. But this is, for now, should be good. And if it's lower than the minimum health factor, and as you can see, the health factor is IE18, then we revert the transaction. So if we don't have 200% over collateralized, we revert the transaction. Okay. Let's jump again to the code. Yeah, over here. So in that case, I showed you the example that we provided $1,000 and we borrowed 500. In that case, it's going to return 1 with 18 decimals. So it's exactly equals to the minimum health factor. But the moment our health factor goes a bit lower, let's say our collateral value is $998 instead of 1,000, then it will be below 1 in 18 decimal points, and that's when this transaction will be reverted. We won't be able to mint any DSC tokens. And so we saw how we deposit collateral and how we mint DSC tokens. We can also redeem basically our collateral to get it back from the protocol, but we'll have to burn those DSC tokens. So we'll need to approve the contract to spend our minted DSC tokens so it can burn it, and then he will send us back the collateral, right? So here we have redeem collateral for DSC. And it's similar to deposit collateral and mint DSC, just the opposite way. So it calls the burn DSC and redeem collateral. Burn DSC first, it's gonna burn our tokens, okay? And it's gonna revert if our health factor is broken. There is another check over here, but this is simply just gonna call the internal burn DSC function. Now, this is the redeem collateral and the burn, so it simply calls the burn. It transferred the DSC tokens from the message sender to this smart contract, and then it just gonna call the burn function, okay? And redeem collateral is gonna send the collateral back to the user, right? So it transfers the token with the amount to the message sender, to the two, and it passes the two from the external functions over here. So we know how we can basically deposit collateral, mint tokens, and we can burn tokens and redeem our collateral back, right? Now we have also liquidate function. So this is in order to keep the protocol healthy. We can liquidate other users that go under collateralized, which means that let's say there is a user that in our previous example provided assets that were $1,000. Now he minted DSC tokens that were 500 DSC tokens, $500, and then he deposited wrapped ETH, and wrapped ETH dropped in price, right? So now his collateral is $800. Now he's under collateralized because his collateral is not 200% of the DSC tokens that he minted, which means that he can be liquidated, which means that another user can come and liquidate this user that is under collateralized because he doesn't have 200% collateral. So we can basically make some profit as the liquidator. We are gonna pay his debt and take his assets. Yes, so we're gonna get his assets and we're gonna burn those DSC tokens instead of him. So we're gonna approve the smart contract to burn those DSC tokens, and we will get the user that is under collateralized, the user that is like underwater. We're gonna get his basically collateral. We are paying for his debt. We are paying his DSC tokens. They will be burned from our account, and we will get his collateral. We will get again in depth to the liquidate function once I will start taking a look at the findings. So this is quite simple smart contract, not too many lines of code, very basic, and debt and like borrowing. It's kind of like lending and borrowing. It's a bit similar to some Oracle manipulation exercises if you went through them in the smart contract hacking course, but a bit different engine, 200% over collateralized and minting stablecoins. So now we'll go through every finding that I reported, but before we do that, I want you to ask questions if there is something that is not clear, and also let me know if it's clear. Please write in the chat in the stream, and then we'll go through the findings that I submitted and analyze every single one of them. This is the other medium issue that I reported. The DSC engine can be deployed without supported tokens. As we saw in the constructor, we can pass arrays with zero length, right? So basically the engine can be deployed, the contract, without any supported tokens, so it will not be usable. So this is another medium issue that I reported. This is another low issue, use of floating pragma. So basically here there is no locked version of Solidity, but it's like we use this kind of sign to show that it's like a minimum this version. So it could be another version that is higher than this version as well. And it's always recommended to have a fixed version of compiler to avoid any errors. This is usually considered a low issue, so I reported this one as well. And we have some gas optimization that we will get on later on. And now we'll start to take a look at these 4 highs that I submitted. So the first high is that WBTC positions can never be liquidated. Okay, this is the first submission that I submitted. And now we will understand exactly why WBTC position can never be liquidated. So let's see. So the protocol is supposed to be deployed with supported collaterals as WBTC and wrapped ETH. Now, the thing with this protocol is that it assumes that all the tokens that will be supported are with 18 decimal numbers, as you can see it over here. Because you see the precision here, it's being used everywhere to determine the token price in USD, and the number is IE18. So we use to multiply with this number, and we assume that the tokens are with 18 decimal numbers. But if we actually go to WBTC Etherscan, we know that WBTC is not 18 decimal numbers. It's only 8 decimal numbers. And because it's 8 decimal numbers, it's gonna make a lot of issues. And actually 3 of the issues that are reported are because we assume that all the collateral tokens are 18 decimal numbers, and we use WBTC, which is 8 decimal numbers. And it's gonna mix up with a lot of calculations, and it makes a lot of issues. And another cool thing that it's kind of like an alpha tip is take a look at the test file. Because what I did, I basically went to the test file. When I saw this and I had this suspicion, I went to the test file and I went to the unit tests and DSC engine.tests, and I searched for WBTC. I wanted to see if the WBTC tests are covered, right? Because if they are covered, I want to see how come it worked, how come you can liquidate users, how come you can mint DSC tokens and deposit WBTC. And then what I found out, these are tests that I wrote in Foundry to check, to do some POCs, but apart from them, we can see that the only section where we are working with WBTC is commented out, which means that the WBTC tests are not completed. All right, so let's see how it works. So we know that WBTC is 18 and 8 decimal numbers, and wrapped ETH is 18 decimal numbers, right? This is wrapped ETH. As you can see, 18 decimal numbers, and WBTC is only 8 decimal numbers. So let's assume that we are a user that want to deposit WBTC to the protocol and start minting DSC tokens, okay? So if we want to deposit WBTC, we know that the contract will be deployed with WBTC as supported tokens. So we will call this deposit collateral and mint DSC, right? We want to deposit BTC and mint DSC tokens. Deposit collateral will be executed first. We'll go through all this check, and then our mapping, we will add the amount. Now, I want to ask you guys here in the chat, this amount collateral is going to be in which decimal numbers? How big this number is going to be? It's going to be with 8 decimals or 18 decimals if we're going to deposit WBTC. What do you guys think? Exactly. It's going to be 8 decimal numbers. So in our mapping, the number that we deposited with this WBTC is going to be 8 decimal numbers. So if we deposited 1 BTC, okay, then it's going to be 1 multiplied by IE8, right? So this is the amount that will be, or simply 1 with 8 zeros, 1, 1, 2, 3, 1, 2, 3, 1, 2. This is the number that we'll have in the mapping, right? 1 with 18 decimal numbers if we deposit 1 BTC. And this token will be transferred, the WBTC will be transferred to the smart contract, and now we'll try to mint DSC tokens, okay? So here we add the amount DSC to mint. Now, what is the amount DSC that we want to mint in that case? Just choose a number. Let's say we deposit 1 Bitcoin and 1 BTC equals $2,000. So how many tokens do you want to mint? We are basically going through line by one, and yeah, okay, let's say we want to mint 200 DSC tokens. Okay, so we deposited 1 BTC and we want to mint 200 DSC tokens. This is 10 times less, so it's pretty good, right? We can mint up to 1,000 based on the protocol description. We can mint 1,000 DSC tokens, but we choose to mint only 200. So this mapping will be updated here with 200. So now we have 200 DSC in depth. Now, before we mint those DSC tokens, we run this function, revert if health factor is broken. And this is where the problem is. So let's see how we calculate the health factor. So This get account information, it's gonna calculate our collateral value in USD to determine how many DST tokens we can actually mint. And get account collateral value, this is where it gets interesting. This is the function that iterates through all the assets that we deposited to the protocol, and it tries to calculate the USD value of them and summarize them into one number. So let's see how it works. It's basically gonna iterate through all the collateral tokens, get the token address, right? Get the amount that we deposited on this token, right? And here, as you can see, I added a comment. WBTC will be with 8 decimals. We went through it already. We said that when we deposited, the amount will be with 8 decimal numbers. So this will be the amount over here. And we will add the value in USD. But before we add the value in USD, we need to get the USD value. So we have to get the USD value, right? We send the token and the amount. So in our example, we're gonna send here the WBTC address, and the amount is gonna be 1 with 8 decimal numbers. Let's see what happens here. Here we're gonna use the price feed of the WBTC token to determine the USD price, okay? So as you can see, we get the price feed of the chaining price feed of the token, the WBTC token. So this is the contract. This is the library that we use, that we wrote. So I'm not going to get now into the library, but this is a library that's supposed to give us the price of Bitcoin in dollars in 8 decimal numbers. Okay, it returns it in 8 decimal numbers, both for ETH and both for Bitcoin. So let's see what happens. We get a price over here. This is the price. And now we calculate the USD value. So this is the price that we got from Chainlink, multiplying it by the additional feed precision. The additional feed precision, if you remember, is 1 in 10 decimal numbers. So we convert it to 18 decimal numbers. We got 8 decimals from Chainlink, and we convert it to 18. Not this one, this one. So we multiply it by the amount. The amount is with how many decimal numbers it's going to be? Guys, I'm waiting for your answer. This amount, this parameter over here, how many? Yes, 8, exactly, because it was taken from our mapping, exactly. This is 8 decimal numbers divided by precision. What is precision? How many decimal numbers is precision? You can see here already. 18, exactly. So this is going to be 18. This is going to be 8, and this is going to be 18. So with how many decimal numbers we're going to be left in USD value? Right, this is 10 multiplied by, sorry, this is 8 multiplied by 10, so which means this is 18. This is the amount, which is in the WBTC case, it's going to be 8, and this is going to be another 18. We're going to be left with 8, guys. This one, this additional price fee precision, this is going to be 10 decimal numbers, right? This amount is going to be how many decimal numbers? 8. This precision is going to be how many? 18 decimal numbers. So these are all the parameters that we have here in the formula, right? 8 multiplied by 10, we add it because it's like in a power of. So this is 18. This is also multiply, and this is divide. So we're going to have here something like this. It's going to be 8 plus 10 plus 8 minus 18, because multiply is like we add decimal numbers, and division we remove. So the result of this is going to be 8 decimal numbers. And this is bad. Do you see where I'm going? Why this is bad? Because in case of WBTC, because this amount is in 8 decimal numbers and not in 18 decimal numbers, the USD value that we're going to get is also going to be in 8 decimal numbers. Exactly. Now, why is it bad? Because this USD value, we always assume that it's supposed to be 18 decimal numbers, but this is our credit in the system. And when it's with 8 decimal numbers, it's so much lower than the actual amount that we're supposed to have in USD value. So when we calculate our WBTC collateral, it's going to be much, much lower number than it's supposed to be. Significantly lower, actually fraction of WBTC. So the system thing, instead of us having $2,000, because one BTC equals $2,000, we're gonna have, I don't know, 0.000002, right? Divided, remove 10 decimals, remove 10 zeros. And this is very bad, because when we calculate the health factor, we use this our credit, our deposited assets in USD we basically divide it by the mint tokens, and the mint tokens is also in 18 decimal numbers. You can see it over here. Let's go again to the calculate health factor, this function, right? We take this collateral adjusted for threshold. So let's see this audit info. This collateral adjusted threshold, how many decimal numbers it's going to have? 8, right? This one multiplied by IE18, and this is going to be also, this one will be IE18. So our threshold is, so this will be canceled, IE18, and our threshold, basically, our health factor is going to be with 8 decimal numbers. So this, in case we minted DSC tokens and we provided WBTC, this health factor will be a number with 8 decimal numbers, which is obviously lower than the minimum health factor, which is 18 decimal numbers. So if we deposit WBTC to the system, doesn't matter how much WBTC we deposited, we cannot mint DSC tokens, because when we try to mint it, the transaction will be reverted, because our health factor, even if we deposit 1,000 Bitcoin and we ask to mint $1, it's 10 times, it's in the power of 10, like 10 decimal numbers lower. That is my first. WBTC collateral cannot be utilized to mint DSC tokens due to incorrect getUSD value calculation. And here I basically left all the references for the calculation, all this function that we went through right now. And I simply explained that in case we deposited WBTC, the getUSD function, which is eventually going to be also the get account collateral value function, will return number in 8 decimal numbers, while our minted tokens is in 18 decimal numbers, which means that always our health factor will be below minimum. And here is by the way, I also added a POC. So you can see that I created a POC over here in the test file. So this is basically the Johnny test that you can see over here. WBTC cannot be used as collateral POC. And yeah, so as you can see here, I deposited 1 BTC, 1 token with 8 decimal numbers. I got the price of the WBTC from the aggregator. Then I calculated how many tokens I want to mint. So I took 33% of my value. So I took the deposit amount multiplied by the price divided by 3. So if I deposit $1,000, I want to mint $333. Now I approve this. I approve the contract to spend our WBTC tokens, and I call this deposit collateral and mint DSC, and I expect it to be reverted. And exactly that's what happened. The transaction reverted, even though my health factor is supposed to be okay. So this is the POC that shows that actually you cannot mint with BTC, you cannot mint DSC tokens. Yeah, it's basically the way that Foundry works. You can basically impersonate users. So when you do vm.start prank, it basically means that every transaction that I will call now will be from the user account. This is vm.start prank. It's Foundry. It's like you do connect with Audit, right? So when you do in the JavaScript file, this, as you can see, the test is in Solidity, not in JavaScript, because in Foundry, we write tests in Solidity. And this is just, instead of doing like ERC mock WBTC dot connect user and approve, like we do in JavaScript with Audit, we can do this. And now, from now on, until we change it, we will sign transaction as the user. I do think it's a high, not a medium, because in that case, the user is losing money. You cannot retrieve this money back. It will be locked in the contract. It's a counting issue in the protocol. So imagine users are depositing WBTC and it's lost. It will be lost forever and stuck in the contract. It cannot be redeemed, right? So, and they cannot get DSC. So both they lose money and both this BTC will be stuck in the contract, because in the accounting, there is no way to rescue tokens. So this WBTC will be locked and the user won't get anything. Yeah, good question. It will work with USDC. Currently, the smart contract, this getUSD function supports only tokens with 18 decimal numbers. It's a very good point. Yeah, it will also work with USDC because it's 6 decimal numbers. By the way, guys, before I show you how I suggested to fix the issue, do you have any ideas of what would be the way to fix it? This getUSD value, because this is where the problem actually is. Okay, we can either add decimal numbers, so multiply, or what can we do else? Here, this is the problem. You see this precision? It's 1E18, and it's constant value. It's supposed to be a dynamic value. So instead of precision, we have to do something like token dot decimals. So in that case, we'll divide the number only with 18. In WBTC, it will be only 8 decimal numbers instead of 18. It should be a dynamic value based on the token, guys, not just a constant precision. This is constant, and this is exactly what I suggested over here. Modify the get USD value. Instead of using this precision, use token decimals instead. So we need to divide it to get the token decimals from the contract and divide this whole price USD calculation with the decimals instead of a constant precision number. Make sense? Yeah, in that case, we wouldn't lose these 10 decimal numbers because we are losing them because we are dividing it by 1 E18, even though our amount is E8, right? So 8 divided by 18, we lose 10 decimal numbers. If this would be 8, then we wouldn't lose these 10 decimal numbers, and it will be normalized to 18 in the WBTC example. And it will be dynamic. So if it will be USDC, then the token decimal function will return 6. So we will remove here 6, and it will always return 18 decimal numbers. It depends on the token decimals. Additional feed precision, we don't need to change because Chainlink, if I'm not wrong, it always returns the price with 8 decimal numbers. So we add 10 to normalize it to 18. But if the Chainlink price feed returns the number in different decimal numbers, then this additional price feed precision need to be dynamic. Yeah. But I think in that case, all of them return 8. Yeah, true. So yeah, but now we don't use unraveled USDC, so I would maybe basically report it as a medium. It's like the USDT one. We didn't deploy it with USDT, but if we will deploy it with USDT, then it could be another issue because this additional flight precision is to normalize the price that comes back from Chainlink. And we are basically assuming that it will be 8. But now I see that you wrote that ample USDC returns 18 decimal numbers. So in that case, it will be an issue. Yeah, the price will be bad. So this also should be dynamic in that case. Now, the second issue that I reported is that user can unfairly liquidate it right after depositing BTC because of this same issue that we got a price in 8 decimal numbers and the health factor is going to be below minimum, even though we deposited 1 BTC and we didn't even borrow. No, we need to borrow, sorry. We need to borrow something. But if we borrowed even 1 token, our health factor automatically can be low, below minimum. And it means that we're going to be subject to liquidations. So what a malicious actor could do, it simply can just monitor the mempool, and every time someone is calling this function, what is this function? 1 second. Every time someone calls deposit collateral, deposit and mint DSC, or everyone, there is a current deposit of BTC, and the moment he mint DSC tokens, doesn't matter how many tokens, they can be subject to liquidated. Even though 200%, they have much more than 200%. Even they deposited 10 Bitcoin and minted 1 DSC, you can still liquidate them because of this price issue. And a lot of users can lose money. So if I'm a malicious actor, I can just monitor the mempool, see the moment people deposit WBTC and mint DSC tokens, I can back run, send a transaction that will be right after, liquidate them, and just get their WBTC. I can steal the WBTC for them, right? Because I'm gonna send here WBTC, gonna send here the user address and the debt to cover. And I don't need to send much debt to cover. I just need to send their debt in 8 decimal numbers, even though the DSC tokens is 18 decimal numbers. So I'm going to send just 0.000 something DSC tokens, and I will get all their BTC from the contract. So we can leverage this liquidate function because of the issue with the WBTC to steal all the WBTC from the users that wanted to mint DSC tokens using this BTC. Make sense? So this is the other issue. The core issue is the same. I don't know if it will be accepted, but it's just a different attack vector. It's basically another impact, right? So users will lose their WBTC right after depositing it to the system. It's the same recommendation, the same fix, just different impact. The first impact is that the users cannot use it to mint tokens, but the second impact is, I don't know if it's valid to be honest, but I just thought about it, like how to exploit it. How, if I was an attacker, how I would exploit it? I would just monitor all the deposits and steal all the WBTC from the protocol. providing very low amount. I will deposit wrapped ETH, right? Get some DSC tokens and use fraction of DSC tokens to steal all the wrapped BTC collateral. It's much more severe, in my opinion. It's the same core issue, but I reported it separately. You mean like, so you mean that user deposited wrapped BTC, he cannot mint, then he can redeem it? You can liquidate yourself. You won't be able to redeem it. You won't be able to redeem it because of the Hell factor revert, the Hell factor calculation, but you will be able to attack yourself. But if there is some malicious actor that monitors the mempool and see your position, and he can just front run you and get your wrapped BTC. You will have to attack yourself and liquidate yourself. So you'll have to deposit wrapped ETH, mint this, and then basically get those wrapped BTC back. Now, for the other question, if it's valid to post different impacts when they have the same issue and the same solution, I'm not sure. We will find out, I guess. So we will see how they will treat it, the judges. I think in this case, it's going to be Patrick. So it's the same core issue, but different outcome, different impact. I don't know, maybe someone can shed some light about his experience when there was the same core issue, but led to different attack vectors and different impacts. If it's going to be accepted or not, I'm not sure. Okay, what you guys can do. So here you can see all my findings. So you can go to the public findings and read through them, because now you cannot search Johnny Time, but you can search the title here in the issue. And for every finding that I present to you, you can just search it here, and then you can see it and go through it and read it through later. In the vulnerability details, there is no POC, but I simply describe step by step what an attacker should do in order to make this profit. So I will send you here on the chat a screenshot with all the findings, so you can just search them later or now. Meanwhile, we have this live podcast. Okay, so the next one, so it's the one that contracts the previous one, which means that wrapped BTC position can never be liquidated. And why is that? So we had the getUSD function, okay? And we have the exact opposite function, which means get token amounts from USD. So in the previous function, we sent like token amount and we got the USD value, but there is another function we can say, okay, we want the amount of wrapped BTC if we give $1,000, and then we get a token amount, okay? This is the function that is being utilized here in the liquidate function, you see? Get token amount from USD. So let's say we want to liquidate a user that has wrapped BTC position. So the address will be wrapped BTC, the user that is under collateralized, and the debt to cover should be in DSC tokens with 18 decimal numbers. So let's say we want to cover $1,000 of the debt. Now we're going to call this get token amount from USD to retrieve the token amount of wrapped BTC that we covered. So we take this dollar number and we need to convert it to some wrapped BTC number. So we send here wrapped BTC address, and here it's going to be a number with 18 decimal numbers because it will be the debt in US dollars in 18 decimal numbers. And let's see what happens here. Get token amount from USD. Different function, same mistake, okay? USD amount in WE, right? This is going to be 18 decimal numbers. Precision is how much? 18, right? So 18 multiplied by 18. Price is how much? 8. Additional price feed, 10, right? So here we're going to have audit info. And here we will have 18 decimal numbers plus 18 decimal numbers minus 8 minus 10. So how many decimal numbers this function is going to return? 18. Perfect. So the token amount that we're supposed to cover when we basically liquidate wrapped BTC position is this number is going to be with 18 decimal numbers. Now you can see where I'm going, right? We sent here 18 decimal numbers, debt to cover. We got here 18 decimal numbers. And look what happens when we try to redeem the collateral, because now we send enough money to cover the debt and we want to get the collateral of the user, the wrapped BTC. And the token amount from debt covered is then we're going to add this bonus collateral. So it will be total collateral to redeem. So this number, 18 decimal numbers plus 10%, this is the number of tokens that we are trying to redeem from the user. So if we go to redeem collateral, what is the first line of code here? What happens here? I want to ask you, what will happen in case we're trying to liquidate WBTC position? Yes, it will revert because of underflow. There will be an underflow, guys. Yes, exactly. There will be an underflow because the amount collateral that we're trying to reduce from the mapping is much lower because this will be 8 decimal numbers, it will be 18. So it will underflow, which means that we can actually never liquidate WBTC from the protocol. So it's going to be locked there forever. We cannot mint DSC tokens, we cannot liquidate. So actually, when I think about it, this finding is invalid because you cannot really liquidate the WBTC tokens. So one of them is probably valid. The other one is probably this one will be valid because also here the issue is not in the get USD value, but in the get token amount, the opposite value that's supposed to retrieve the token amount from the USD value. So I guess this one is valid high, and this one is probably going to be rejected because it's not true, because we cannot really liquidate users. We will see, but now you get where I'm saying. It's like the same issue, different function, different outcome. It's issues that are happening all the time. Mistakes with decimal numbers is something that is very common because it's something that is like hard to forget and hard to grasp sometimes. And sometimes it's like external factor that is like unexpected when you add a token. There was a hack. I don't remember which protocol it was, but they added like a contract with 10 decimal numbers instead of 6, and there was a huge hack because of that. These decimal numbers mistakes happen all the time, also in big audits, in like real exploit, black hat exploits, in like bug bounties. Yeah, they are very common. And this is just one example, but there are a lot of examples. Just go to Solidity and search for decimal number or decimal calculation. You will see a lot of issues that are about decimal numbers. Okay, let's move on to the next high, and this will be our last high for today. Users can be liquidated when their collateral value significantly dropped. And for this, I made also basically a kind of, it's not proof of concept with code, but I made a scenario to show the problem. So in certain scenarios, when the prices of wrapped ETH or wrapped BTC experience a significant drop, under collateralized positions become impossible to liquidate due to an arithmetic underflow. So it's similar to the arithmetic underflow that we had before, but not because of decimal issue, because the price significantly dropped. This issue possesses a denial of service risk to liquidate function, rendering it ineffective in such situation. As a result, under collateralized positions remain unaddressed, putting the protocol at financial risk. So if someone has a position of wrapped ETH and wrapped ETH went significantly down in price and it wasn't liquidated, and someone is trying to liquidate it when it went down 50%, then it will underflow and this position will not be able to, no one can liquidate this position. Okay, so user one deposits 1 ETH, and let's assume that the ETH price is $2,000. Then his total collateral is $2,000, and he's trying to mint 1,000 DSC tokens. Now, he used all his collateral because he can mint maximum 1,000 DSC tokens. Now, let's assume what happens if ETH price dropped from $2,000 to $500. In that case, the health factor of the user is below minimum, and he can and should be liquidated, right? Because his credit is $500 and his debt is $1,000. It wasn't changed. Now, user 2 comes to the protocol. He deposits for ETH. ETH price dropped to $500. His total collateral is the same as user 1, 2,000, 4 multiplied by 500, and he mints again 1,000 DSC tokens. Now, user 2 tries to liquidate user 1 by covering his 1,000 DSC debt. Because you can see that he has 1,000 DSC debt and the ETH dropped significantly. So even though it wouldn't make sense to get, because he will pay $1,000 to get to 1 ETH. So, but you still see that his position is $1,000. So we'll call it with wrapped ETH, with user 1, and with 1,000 DSC tokens. Now, the get token amount from USD, how much this is going to be returned, this function that returns the token amount from the USD value. If we send it the wrapped ETH token and $1,000, and we assume that ETH price is $500, how many tokens we will get? What will be the result of this function? 2, right? 2 ETH, right? Because 1 ETH is $500 and we ask $1,000. We get 2 ETH, and this is basically the ETH that should be delivered, redeemed from user 1 to user 2, plus 10% bonus, because he has 10% liquidation bonus. So it will be 2.2 ETH, right? We will call the redeem collateral for 2.2 ETH. And again, we will have an underflow because the user deposited 1 ETH, and now we're trying to basically decrease from his mapping 2.2 ETH. So we cannot liquidate him. But this is not, it's just the way it works, the liquidation is not okay. Because first of all, it doesn't make sense that user 2 will call it with 1,000 DSC tokens when ETH is $500. So we need to call it with a lower number of tokens. It will be reverted with underflow. And this is not like a wanted state. And in that case, it's not pretty, I don't think it's high, because when I revisited it, it can be liquidated, but we need to send much lower amount of DSC tokens compared to the current price of wrapped ETH. So because we know that his position is 1,000 DSC tokens, we don't need to burn 1,000 DSC tokens. We need to burn less DSC tokens to get his ETH, right? Let me think about it. Let me think through about it. You can meanwhile take a look at this submission or take a look at the code and try to think about it yourself, because now I don't know why, but I think there is another issue here. Because we want to cover his debt. His debt is 1,000 DSC tokens, and we want to cover this, and we want to get his 1 ETH. But we cannot really cover his whole 1,000 DSC tokens. We can cover only 500 DSC tokens, right? This is the maximum amount, because if not, actually less than 500 DSC tokens, because we add here 10%. And if we try to cover, and if this number will return any number that is bigger than 1 ETH, which is his deposited collateral, the transaction will be reverted due to underflow. So basically, we cannot liquidate the user with all his position. So he will be left with some DSC tokens, and we will basically burn them. But he will lose his ETH. Yeah, it's a bit messy here, but there is a problem with the liquidate function. So I suggested 2 solutions. One solution is to get token amount from USD. Make sure that this token amount that we're trying to redeem is not greater than the amount that he deposited, the user that we are trying to liquidate. Because if we are covering 2 ETH and he deposited only 1, it will be an underflow. Now, if this condition is true, which means that this token amount that we are covering is lower than the amount that he deposited, or the same amount, then we're just gonna burn the whole DSC tokens and get the collateral. But if it's false, if it means that basically the amount that we are trying to cover is, and that we are supposed to get from the protocol is bigger than the amount that this user deposited, we're gonna reduce the DSC amount that we want to burn. So basically, we're not gonna use all the amount of the collateral. Sorry, we're not gonna use in the liquidate function. We're not gonna let the user cover all the debt of the user, but only the partial debt that will be corresponded for this amount of tokens that the user is actually owning the protocol. Because if not, again, this redeem collateral, if we are trying to redeem collateral from the user that is bigger than what he deposited, it will revert and we will not be able to liquidate him. Always lower than this balance, and which means that also we need to adjust this whole liquidate function to burn less DSC tokens, because the debt to cover we can add here after we get this one. We need to make some kind of if statement. If total, not actually total amount from debt cover, we need to make sure that this one, total collateral to redeem, should be greater or equal to the debt of the user in this token before we call this redeem collateral. And if it's bigger, then we need to redeem less collateral and burn less DSC tokens. So the way I found this issue is simply just writing like scenarios. Okay, so this is my audit markdown file, as you can see. So along with adding comments on the code itself, I have this file on the side where I basically go write overview about every contract, and here I basically make scenarios on the side. So what if user 1 deposit this and the price is this, and then the price went down to this, and then user 2 deposit this. So I'm trying to cover all the states that are available that can happen, which is sometimes hard because this is a simple contract. Imagine how many potential states could be with a more complicated contract. Imagine what happens if this contract would support just more tokens. It already makes it more complicated. What if it's like more advanced system? So it's something like that. It takes time to do, but it's very useful to create these kind of scenarios and say, okay, what if user deposit X ETH? What if he deposit less ETH? It's kind of like making invariant tests in your head. So it's very useful, and that's how I found this issue. So this is one very simple thing: use not equals 0 instead of lower than equals 0, because in unsigned ints we don't have negative numbers, so there is no reason to use lower and equal to 0. It will require a bit more gas. This is one gas optimization. There is another recommendation here: ending user here function in Liquidate, which can be removed to save gas, okay? Because in Liquidate, we reduce his mapping amount, his debt. We always reduce this number. So that's why we always reduce this number. And this health factor is affected by this number. So the end health factor can never be lower than it was in the beginning. So this check of calculating the health factor over again is just going to add a lot of gas to this Liquidate function. So I just suggested to remove it. We use the transfer from and we check the return value. This is not necessary because the DSC token is an immutable token that we wrote. It's not some kind of external token that can be changed. And therefore, this will always return true. If it fails, then it will revert because we follow the IRC standard. We use like Solidity version 0.8 plus. It's like a known token. It's not like an external token that can be added through governance or something. That's why we don't need to check the return value over here. So this check can be removed to save gas, this kind of success return value. And the same thing happens both in burn USDC and I think also in mint USDC. There is another small trick to save gas with this function. Get account collateral value. As you can see, we have a return named variable, but we also have return statements. It's not necessary because if you have this kind of thing in your function, it's automatically gonna return this variable, right? This total collateral value in USD. You don't also need to define it. So here they don't define it in the beginning, but he used the return statement, and this is also redundant. It's not necessary. So this is another recommendation. And the last one, use name returns. So this kind of pattern of using name returns is also saving gas instead of using return statements. And there is this function, get amount from USD. Get USD value, sorry. Get USD value. So here they don't use return statement, but they just use this, but they can just instead, they could just do get US return this uint USD value and remove this return statement. And then we will save some gas. Yeah. So these are just some small tricks and gas optimizations where you can report in this case. I just saw it, I wrote a comment and decided to report them. Yeah, I'm not very focused on gas optimization. I don't know, I felt like reporting this. Here it was more interesting in the Escrow Contest to report gas optimization because the code was very solid and very secure. So I guess we will not cover the Beetle Finance contest, but we'll go through the Escrow Contract Contest because, first of all, I didn't spend much time on the Beetle one, and second, there was so many, the codebase was so bad, and there were so many security issues that I at some point I just felt tired reporting them, and they were just too obvious, and the pot was very small, so it wasn't that interesting and time worth to spend in reporting them. But the CodeHawks escrow contract was more interesting because it was pretty solid, pretty secure, and I think even this medium and gas that I reported might be more worthy rather than all of these IE issues that are probably detected by many people. Like they didn't follow simple checks affect interactions. There were these contracts were all over the place, this Beetle Finance. So I just spent 2 hours on it and I just reported some findings and I just left it. I didn't even look at all the contracts. It really depends. It's a good question. So the question is, would a code base with a lot of issues will be a good one for first time audit. It really depends. So I have a friend that completed the course and he participated in a Libra finance audit. It was very bad code base and he reported a lot of vulnerabilities, and he was able to take the 7th place and get $1,700. It was his first contest, so this is super cool. I'm super happy for him. And in that case, it worked, but I remember in the previous USSD contest in Sherlock that you saw, I don't know if you know, but I reported like 5 high valid severity issues, and I got $4 for 5 high valid issues. This is less than $1 per issue, and also after the escalation phase, it was reduced to 70 cents. So I got 70 cents for 4 high valid issues because it was a small code base. It was very small pot and very obvious, like high issues. There were so many issues, so it was diluted. So I just thought that it wouldn't be very interesting and doesn't worth my time. It really depends on the contest, on the pot, of how many participants there are, how big the code base is. Yeah, so it's every case. I just didn't feel like continuing this one. Any more questions before we move on to the escrow contract, which is more interesting? And now we're jumping to the escrow contract. So the cool thing about this escrow contract that it's the contract that's going to be used by CodeHawks for the marketplace. So you can provide auditing service, and buyers can come and look for audit services, and they can pick you as a personal solo auditor through CodeHawks marketplace. And this smart contract should be the escrow contract that will lock the money between the buyer and the seller. So the buyer is locking the money in this contract, and the seller is getting the money while the work is done. And this contract is very well written because it was written by the team, I guess, either by Patrick or by Hans Fries or I don't know who, but it was pretty solid. The pot was pretty high, $40,000, and I didn't find any high severities there. There is only one medium severity. I'm not even sure that it will be accepted. Yeah, it was written by Patrick and Alex. Yeah. Sometimes just some of the exercises that you went through the course, you can really find those same issues in Codebases. Sometimes it's a bit more challenging, but that's why we are here, right? We're improving every single day. I highly recommend you really jump to the water, try those contests. Now, if you didn't participate in them, try maybe to read my findings, to do shadow auditing to them, see if you can find something before you read the findings, but eventually you will get there. You just have to keep working hard, improve this muscle of like auditing, of reading code bases fast and understanding the different state transitions, and it will be awesome. In Beetle. Yeah, I reported this one as well, but I assume there are like 200 more students that reported the same one, so yeah, I'm sure it's going to be very diluted. The slippage issue, and the block timestamp issue that we also had in the USSD contest. Is there anything one could lose in participating in such audit? Yes. In Sherlock's, you have penalties if you submit too many invalid issues. There are many people that are just spamming the judges. They are just submitting like invalid issues that they generate from ChatGPT. They are invalid. They are not written properly. So never do that. Remember, on the other side, there is a human being reading your report. So they started because they don't want the judges to be spammed, because the judge time is valuable and they are paying money to those judges. And imagine now a judge that get like 1,000 issues that are like generated by GPT and they are invalid and they are bullshit. So he just spent his time. So what they started doing in Sherlock, they're gonna give you penalties for invalid issues that you report. So you want to make sure that really every report that you submit is high quality, well explained, and is actually valid. Don't generate something from GPT and expect to be rewarded, because they also might penalize you, and in the next contest it will be deducted from your price. In CodeHawks, they have, I didn't went through the whole documentation, but they have something similar. So you have some kind of, if you submit too many invalid issues, they might ban you from the platform completely. So it doesn't mean that, I'm not trying to scare you and tell you don't submit issues, but just really think through and invest in your reports, right? Make sure that the issue is correct. either write a POC or go through like the state transitioning, make sure that it's actually valid, and also invest some time in writing the report. Because also if it's a good report, if you explain it correctly and the structure is good, you might get even bonuses because it will be the selected for the final report, the selected issue for the final report. So really don't submit bullshit stuff to contest to save the time of the judges and that you will be respected and treated more seriously. Yeah, it's cool. Yeah, if your issue gets selected, 1.5x, so you get almost 50%, 40% more in the reward. Yeah. Cool. So this is the escrow contract, and escrow is very simple. You have a buyer, you have a seller, and you have arbiter. What is arbiter? Arbiter is a third party that in case something went wrong between the buyer or the seller, the arbiter comes into the picture and he decides how much money the seller is actually gonna get from this initial offer. So this is the context that this contract is based on. Okay, and what we will do now, we will go... by the way, another cool thing that you can do is forge coverage. Remember that I said before that I saw that there are problems with WBTC because I saw that WBTC wasn't covered through the test. So this is awesome. If the repository, this command is awesome if the repository is with Foundry, because you can just run forge coverage and it's going to tell you every contract, what is the test coverage for this contract. So you can see this escrow is very well tested. We have two main contracts, escrow.sol and escrowfactory.sol, and they're like perfectly covered. You see, like all the functions are covered. Also in the stablecoin, if you do forge coverage, you will see the same thing, that it's very well covered. The test cases, let's let it run a bit. And unlike the BDL, if you run here forge coverage, look at this one. Look, BDL, fees, lender, staking, all these contracts are these ones, they don't have any test for these contracts. These three ones, the lender has 81% test coverage. So this is just how you can see how well written the code is, you know, how well tested it is, the unit test. Here we don't barely have tests, unlike these two repos where we have good tests. So let's open the escrow one. And there we go. This is the escrow repository. We have two main contracts, escrow and escrow factory. Yeah, moving on to the escrow contract. So this is the escrow contract, and let's see what we have here. So we have two main contracts, escrow factory and escrow.sol. So the way it works that, let's say you want an audit to your smart contract. So you come to CodeHawks and then you send a transaction to escrow factory. Okay, this contract. You call the function uEscrow. You set the price that you want to pay for the audit. You set the token. So the token could be any ERC20 token. Basically, you can pay in USDC, in USDT, in WBTC, in basically any ERC tokens. It can also be a scam token because there is no check for the token. So you can set any token that you want. Who is the seller? So it's already like when you pick the seller from the marketplace, you're basically gonna provide this seller address. Also, it's a marketplace, so every buyer and seller has an address. And who is the arbiter? The arbiter is the guy that gets into the picture when there are problems. And they're gonna suggest that it's gonna be CodeHawk as the arbiter if there is a problem between the seller and the buyer, but anyone can be the arbiter. They will suggest it, but you can choose any other arbiter that both you trust, and this will be the fee. So in case the arbiter need to work and decide who gets the money, he gets some kind of fee of this price. So this price either goes all to the seller or goes partially to the seller or to the buyer, and also partially to the arbiter because he had to get involved and work, and this is the salt. So to make sure that the contract, to add this to the contract address, to the contract generation, so the address will be unique. So we won't have two contracts with same price, same token, same seller, same arbiter. It will be the same address. So we add this salt. Now, why do we need salt? Because we're going to create a new contract. Every time we have a new deal between two buyers and seller, we deploy this escrow contract. That's why it's called escrow factory. Like Uniswap V2 factory that you're familiar with. If you went through the DeFi crash course, you know that every time we create an LP, liquidity pool, a pair, then we go through the Uniswap factory to create a new contract, new pair contract. So the same thing happens here. And we compute the address in advance. Because we use create2 opcode, we can predict the address of the smart contract that we are going to deploy based on the parameters. So we have also this function, compute escrow address, where we basically send all the parameters. One of them is also the buyer. Who is the buyer, by the way, guys? Who is the buyer? Because we didn't get it here as a parameter. We didn't get it as a parameter for new escrow. So what is the address of the buyer? Exactly, message sender. Message sender is the buyer, the one who calls the function and wants to start this new escrow thingy. So he's the buyer, and here we can calculate in advance. You can also, they left a reference here of how they calculate it. So it's from the Solidity docs, how to salted contract creations with create2. And then what we do, we send the tokens before we actually deploy the contract. So this new command is like create2. It's like introduced in some, I don't remember which version of Solidity, but this is like using create2. We are deploying a new escrow contract. We see here that we import it, right? So we import it to the factory, and every time someone calls this new escrow, we deploy it with all the parameters. So the first thing that I wanted to do, I just went through all the parameters and make sure there are no mistakes with a parameter order or anything. And I highly suggest you to do it, because here we have a lot of parameters and we pass them between different functions. So maybe here the order is different, or maybe here the order is different, or maybe here the order is different, or here. So I really went through every single parameter to make sure that it's like in the right place. I don't know if you did it as well, but this is just one tip that I do usually when you have a lot of parameters and we pass them between functions. Now we transfer the tokens to the computed address, and then we deploy a new escrow contract. We make sure that the address is equals the computed address, or we revert the transaction, and we return the newly deployed contract address. Pretty simple. This is the factory contract. I didn't find many issues. You know, a lot of people reported this front-running issue that you know, people talked about it. I saw in the CodeHawks Discord that you can front run, but I think it's a non-issue and it's going to be ignored. I don't know if you guys found any other issues. Please let me know. I didn't find any significant issues rather than front run. So you can basically front run this contract creation, send the same salt and front run it. Yeah, exactly. So front running was like a non-issue, so it's going to be probably ignored. But what they didn't do here is that basically deploying this new escrow contract gonna take a lot of money, especially if it's going to be on Ethereum, because you deploy the whole logic over again and again. And if you've been through the call attack section, we talked about minimal clones and minimal proxies by OpenZeppelin. Why they didn't use it, I don't know, but they can save a lot of gas of every escrow contract deployment if they just use minimal clones. And again, also predict the contract address using minimal clones. They can use the clone deterministic and predict the deterministic address in OpenZeppelin clones factory in order to predict the contract deployment in address. So instead of deploying every time the whole escrow contract, they can use OpenZeppelin clones to just deploy minimal proxies, and the contract with all the logic will exist only once. And the proxy is the one with the state that will hold the tokens and all the state parameters like seller, arbitrary, fee, whatever. But the actual logic, everything will be deployed only once. So every time someone deploys new escrow, he will save gas. Did you guys also report this? This is a very interesting one, and it's going to save a lot of gas. I don't know if it's going to be rewarded with some money, if it's legit or not, but I think it's a good suggestion. What do you guys think? Yeah, I don't know how come they didn't think about it, or maybe they did and they decided not to go this. It's more like of a design decision, but yeah, I hope it will be rewarded because it's going to save a lot. I hope they will actually implement it because it will save a lot of gas for every time we deploy a new escrow contract. So this is one of report, just to use OpenZeppelin minimal clones. You know, it doesn't have to be too sophisticated, but you just see a problem that you're aware, you know, you can save a lot of gas. I just say it, you know, I don't need to be just the more knowledge you have, if you would listen to the class, you would be aware of like what are clones, what are minimal proxy, how they work. The moment you see something like this, damn, you can give them value to the protocol just by telling them, guys, don't do that way. Use minimal proxies. And you can explain them also why it will be cheaper every deployment. Okay, the seller have no way to get 100% money, no matter they are 100% correct. Yes, let's go to the escrow contract, because now we need to understand like how it works, to understand this issue that you reported, which might be legit. So this is the escrow contract, okay? We deploy it every time we have a new deal, right? So this is the price, the token contract, the buyer, the seller, the arbiter address, and the fee. The fee is U256. This is the state of the contract. So if you go to the interface, you can see this escrow contract can be in 4 different states. Created is 0, right? It's enum, so it starts from 0, 1, 2, and 3. So 0 is created, which means that the contract was created and we just started our deal. Confirmed is basically when the buyer is saying, okay, I got a service, I confirm, let's release the fund to the seller. Disputed is like either the buyer or the seller, they can call the escrow function and start a dispute. Say like something is wrong, okay? Either the seller is like didn't do anything or the buyer didn't do anything. So they want to start a dispute. In that case, that's where the arbiter come into the picture. And resolved is the state that the arbiter already did his job. He decided who gets what. And this every escrow need to be either eventually confirmed or resolved. Okay, makes sense? This is the last state. So these are the 4 states that this contract can be. And this state variable is basically the variable that will hold the state. It's state enum, but it's basically a uint8. It's a number between 0 to 3. Now, this is the constructor that will be triggered right after deployment, as you can see, because we send all these parameters. So the constructor will be executed. We make sure that the token contract is not address 0. Or we revert, so we won't be able to deploy it. It's important to understand that every time revert happens, it means that this transaction will be reverted, this new escrow, because the contract creation will revert. So the whole transaction for the new escrow and the factory will be reverted. So if the token address is 0, it will revert. If the buyer or the seller is 0, it will revert. And if the fee of the arbitrary is greater than the price or equal to the price, then it's too much, so it will be reverted. And also if the funds weren't sent here, so if there was an issue here with the safe transfer form, then it will be reverted. So we send the funds to the pre-computed address before we actually deploy the contract. We send it here, if you look at it. And this is a very interesting approach. I think it has some issues, maybe, I don't know, but maybe someone reported about it. But you send the money to an address before you deploy the contract, because you can predict that this address will be the contract. So here they check that the balance is already in the contract and they set all the state variable. So this is how it works. And here, as you can see, I added an audit OK comment. So the next time I see this line of code, I understand that it's okay, right? So through reading the code, I add these comments. Funds are being sent prior to deployment. So I know that this check is like, why the hell they check the token balance in the constructor? Okay, because they sent here the tokens before they actually deploy the contract. Make sense? Which brings me to the medium issue that I reported that I'm not sure if it will be accepted. I hope so. But what issue do you see here? Guys, I want you to take a look here in the constructor and what kind of state is not good and it can happen. Look at this required statements. What is missing? Something is missing, in my opinion. I don't want to show you. I want you to come up with it by yourself. Yes, exactly. Buyer can be arbiter, not only buyer, also seller. There is no check that the buyer and the seller are not the arbiter. And the whole idea with escrow is that the arbiter will be a third party, right? So we can deploy a contract where seller is the arbiter or buyer is the arbiter, or all of them are the same account, same address. And I think this is a medium issue because if we deploy an escrow contract with the same address as buyer and arbiter or seller and arbiter, we basically lose the meaning of the contract. So I guess it's medium. Okay, so in that case, the seller will not provide the service. Yeah, makes sense. Probably it will be rejected, but I don't know. We can just add this test over here, another require statement, buyer not equal arbiter, seller not equal arbiter, and that's it. Why do we need to get into these corners if we can just verify it on chain on the contract? It's just another require statement, and they already spend a lot of gas deploying the contract every time. So another require statement won't make that much of a difference. Yeah, the code base a lot of off-chain trust. True. This whole idea of escrow is basically off-chain trust, because also there is this function confirm receipt, which is only the buyer can call. It basically says, I confirm the seller delivered the job. Now he can never buy it, confirm it, right? Because you can never decide never to call it, but he will not be able to get the money back. The only way for the buyer to get the money back is through a dispute and through the arbiter. That's why I think this is actually a valid issue, because this lets the seller to get the money back. If you just do not confirm the receipt of lets the buyer get the money back. Because if the seller did not provide and he doesn't confirm the receipt, the money is still stuck in the contract. He cannot retrieve it back. But if he's also the arbiter, he can initiate the dispute as the buyer, and then he can resolve the dispute as the arbiter. We have these modifiers, only buyer or seller, only arbiter. So he can say, as the buyer, initiate the dispute, I didn't get the money, and then he can just say that the buyer reward is 100% and get the money and scam and rug pull the seller. Yeah, there was another require statement that arbiter could be address 0. There is no, if you can see here, there is no if statement that arbiter is address 0, which means that we can create an escrow contract with arbiter without arbiter, because the arbiter would be address 0, which means that we can initiate a dispute, and this dispute can never be resolved because we have here this modifier and the arbiter is address 0, so we can never resolve it. And they said I saw it, they said that it's okay that a contract can be without arbiter, but I don't think it's okay. I wouldn't design it that way, because if there is a disagreement and the buyer will never call the confirm receipt, this is the only way to release the funds. And with arbiter, we have another way to release the funds from the contract. So I don't know. It's questions about like how real escrow should be and how it should be designed. But if I would design it, I would require an arbiter in that case. And I would require that the arbiter wouldn't be the buyer or the seller. Yeah, it's pretty solid. There are not many issues because the logic is pretty simple and there is not much functionality here. There's not much you can do with the contract, but this whole thing with the arbiter, there isn't, it could be seller and buyer. This is the only thing I reported as medium. I don't know if it will be accepted. And I have another gas optimization issue here. Let's see if you guys all also reported it. So let's see, it's here in the resolve dispute. So this resolve dispute is basically when we have a problem between the buyer and the seller, and the arbiter is basically making a decision as the judge, and he says, okay, let's say the contract was $2,000 and I think that the seller delivered just 50% of the job. So that's why the buyer is going to get $800 back. My fee is $200 and the seller is going to get his $1,000 for the 50% job that he provided. So he calls this function with $800, right? The fee that he gets is $200. So we make sure that we get basically the token balance. We calculate the total fee, which is the buyer awards plus buyer fee. And then we make sure that it's greater than token balance, or we revert. So this is basically the balance that the escrow contract has right now. We change the state to resolved and we emit an event. Now we need to pay money to whom? So this is the award total fee, the buyer award and the arbiter fee, but we need to pay the leftover to the seller, right? So we need to check how much money there is still left in the contract to pay to the seller, the one who provided the service. So we have some if statements. If buyer award is greater than 0, then we send the award to the buyer. If the arbiter fee is greater than 0, we send the fee to the arbiter. Then we get again the token balance, and whatever left we send to the seller. Now, this is not efficient in terms of gas. Why it's not efficient in terms of gas? Because we we get a token balance twice. We access the storage, the mapping of the balance of the token in the token contract twice. And this is not necessary because we always know we can take this token balance that we already calculated and we can just reduce this total fee, right? We can put it in a new state variable, let's say like leftovers, like seller leftovers, and seller leftovers equals, so you can see I did it here. So we don't need to retrieve the balance again. We can just make a new variable, leftovers equals token balance minus total fee. And then if leftovers greater than 0, we just send it to the seller. So we can save some gas because accessing storage variable, especially if it's in mapping, which is the case in token balances, is more expensive than just simple arithmetic operation, which is just simple in terms of gas. So this is another gas optimization suggestion that I put over here. More logical one, I think of the functionality and I think how to save the gas, and I think it will be rewarded because it's like, I don't think many people reported something like this, and there are no many like high issues or medium issues in this contract. So I hope that these two gas optimization suggestions will be awarded and they will actually improve the logic to save gas. Anytime someone deploys a new escrow contract, or sometimes every time someone tries to resolve a dispute, because we can save here and there gas. And let me know what you think, guys, about these issues. I reported only 3 issues, these 2 gas ones and 1 medium one. What do you think about them? They're legit, they will be accepted or not? Did you report something else that might be interesting that you want to show us? I don't think so, because I think that accessing mapping is more expensive than creating a new memory variable and doing a simple arithmetic calculation. But we can actually test it. I guess, EVM opcodes, and you can see, like, I don't know which is the exact opcode. I think S storage load. So this is the opcode, storage load, right? Because we load something from the storage when we get the mapping variable. And this is quite expensive compared to like add, or when we do calculation, we use add, I guess, or sub, because we reduce something. Yeah, this is supposed to be cheaper. So you can see sub is 3 gas units, right? Sub, when we just divide one number with another. I don't know if with the overflow checks, in Solidity Zone Parade, it's going to be probably more expensive, but as load, you see either 100 or 2,100, much more than just arithmetic operation. You read from storage, it's more expensive. Good question. How long did I spend auditing those code bases? So it wasn't like a concentrated work. So I can assume that if you like combine the hours in total, it would be around like 2 days for everything. But I worked like, 1 hour here, 2 hours there, which is not very good in my opinion, but I was busy with a lot of other things. If it's like working on a final exam for you, if it's like content creation, videos, posts and stuff, or like just being active in the community and talking with people. So I had other things, but I was able to like invest like 1 hour a day, 2 hours a day. And I think in total, if you calculate everything, it's around 2 days. Yeah, so it's exactly, it's like what happens if there is no arbiter, then the funds will be, the only way to retrieve them is through confirm. So the funds won't be stuck because the buyer can always call the confirm function. So I wouldn't say it's high. I don't know if it will be accepted because they said that arbiter could be 0 and it's okay. But yeah, in case the arbiter is not set, the only way to get the money out is through confirm receipt. So I'm not sure if they will accept it, or it's definitely not going to be high, but maybe it will be accepted. I don't know. Where there is no arbiter and buyer is dissatisfied with the seller delivery, but escrow contract is created with no arbiter. In this case, there is no way for the buyer to retrieve their funds sent to escrow contract, since both functions, initiate dispute and resolve dispute, cannot be called. Yeah, fair point. I agree. Yeah, I agree. Fair point. It's like it loses a bit the idea of escrow, right? Because if you don't set an arbiter, there is no way to get the money back. So eventually the money will be released. But what's the idea of the escrow contract? So you delay the money or you never call it and the money will be stuck. I agree. It's like some kind of issues with this arbiter thing. Yeah, so we are, maybe there will be more chapters. On my backlog is also to create another more advanced course, but it's not going to be soon. It's going to take a while, and maybe there will be some more guest lectures in the course, and maybe I will add some more exercises here and there, but it's not going to be very soon because now my focus is to basically finish with the final exam and their certification and help you guys like do some business developments with auditing companies. So, this certificate will be accepted and will be validated, and it will help you guys to maybe get your first internship or junior position. So this is like my main goal and focus right now, do these collaborations and finish the whole certification and final exam thing. But once I'm done with these high priority tasks, maybe I will find some times also to content creation. So I want to publish content and free content on my YouTube channel and articles and CTF walkthroughs and stuff like that. So you can enjoy it, and people that also don't have money to purchase the course can learn from those free contents. But I will definitely, it's also on my to-do list to add more chapters and add more exercises, or maybe to collaborate with more professionals in the field to introduce more guest chapters. So yeah, you can expect for more in that manner, and also live sessions. You see, every time I have an opportunity and I have some free time and I see there is opportunity of like a beginner-friendly contest, I'm participating so I can make those sessions later. So I'm glad that it's valuable and you enjoy them, and it basically gives me more motivation to do more of this. So please let me know if you have any feedbacks or you want me to improve something or change something, I don't know. And yeah, I will be more than happy to do these live sessions, interviews, and maybe even bring some of the guest lectures here to the community. So thank you so much, guys. It was a pleasure. I hope that you enjoyed and you learned a lot of new things. This session also will be uploaded to my YouTube channel if you want to rewatch it or like take your time around it. And thanks again. See you next time. Enjoy the course, enjoy your journey. Remember, it's like, enjoy the process, okay? Don't always expect rewards. You really need to work hard and grind. And the more you do that, you will see the results will come. Like, just your skill will get better and better and the results will come. So thank you so much and have a great week ahead. Bye-bye.